In this question, a scientist is investigating a reversible reaction involving ammonia, oxygen, nitrogen dioxide, and water at 3190 Kelvin and 1 atm. So here's our equation. We can see we've got that reversible arrow showing that this reaction can go forwards and backwards. We're also given a value for K here. K is the equilibrium constant. The equilibrium constant is the ratio of the concentrations of our products and reactants at equilibrium. So what that means is it tells us, are we going to have roughly the same concentrations of our reactants and our products? Are we going to have much more of our products, much more of our reactants? How is the mixture of our reactants and products going to look when we're at equilibrium? So we've got three options. The first option is if K is equal to 1. If K is equal to 1, that means the ratio between our products and our reactants is 1. So that means that neither products nor reactants are favored at equilibrium. So what that means is we're going to have roughly the same concentrations of our products and our reactants. If K is less than 1, that means that we have smaller concentrations in our products and higher concentrations in our reactants. So that means our reactants are favored at equilibrium. And if K is greater than 1, that means our products are favored at equilibrium, which means that the concentrations of our products are going to be much higher than the concentrations of our reactants at equilibrium. So let's go ahead and try this question. So in this one, our K value is 4.84 times 10 to the power of 12. So times 10 to the power of a positive number means we have a really big value. So if we were to compare K with 1, in this example, K is much greater than 1. So first we'll ask, are the products or reactants favored at equilibrium? So looking down here, when K is greater than 1, our products are favored at equilibrium. And lastly, we're asked how the concentrations of the products and reactants compare after the reaction has reached equilibrium. So when we get to equilibrium, we know that K is much greater than 1, which means our products are going to be really highly favored. So what that means is we're going to have much more products than we have reactants. Let's try a couple more of this type. So again, in this question, we have a reversible reaction involving carbon, water, carbon monoxide, and hydrogen at 890 Kelvin and 1 atm. There's our reversible reaction arrow. Here's our K value this time. It's 0.192. So that value is just a little bit less than 1. So here K is slightly less than 1. So looking at our table down here, if K is less than 1, that means that our reactants are favored at equilibrium. So what's favored at equilibrium? The reactants are favored. So that means we're going to have more of our reactants than our products. So a higher concentration of reactants. But since K is only slightly less than 1, it's not a really tiny number, it's just a bit smaller than 1. That means we're going to have slightly more reactants than products. Lastly, in this question here, we have a reversible reaction involving fictional substances. Again, we're given the equation with that reversible reaction arrow. This time we're called K is equal to 1. So looking at our table down here, when K is equal to 1, neither reactants nor products are favored at equilibrium. So what's favored at equilibrium? Neither. Because when K is 1, that means the ratio between the concentrations of each is the same. So how do the concentrations of the products and reactants compare after the reaction has reached equilibrium? Well, we're going to have similar concentrations of our reactants and products because overall, we're going to have to end up with the ratio between them being the same. So that's what K equals 1 means. So in these questions, all you need to do is look at the K value, see if it's less than 1, in which case reactants are favoured at equilibrium. See if it's equal to 1, in which case neither reactants nor products are favoured at equilibrium. Or see if it's greater than 1, in which case products are favoured at equilibrium.